So, I welcome you all in this session of Material Science and Engineering course. And today we will learn something new, something interesting topic. Okay. So far, what we have learned the um, different phases which are present in different regions of iron carbon diagram. Okay, and we have seen how the microstructure get evolved during the solidification process. We have seen how the eutectic point at eutectic point above eutectoid point what is the microstructure, and below eutectoid point what is the microstructure. Similarly, we have seen in hypereutectoid steel at different regions, and in hypoeutectoid steels in different regions. Okay, and we have explored its engineering applications depending on the phases present in the component, depending on the phases present in the material. Okay, so far what we have learned, this these things we obtain on the phase diagram, and phase diagram is obtained from the equilibrium phase diagram. What is the meaning of this? That if we are getting perlite, then we are getting this perlite uh, after slow cooling, right? But in whole iron carbon diagram we have not included time as a parameter on which the microstructures depends, right? So it is very important to understand how the solidifications happens in a liquid metal, right? And what is the effect of time on this solidification. We will learn we will learn that if the time is less, how the microstructure, which kind of microstructure we will get. And if time is very slow, okay, then we will see what would be the microstructure in the final material. Okay, so before exploring this, let's try to understand some basic and fundamental concept. Okay, now suppose you have a container, okay, and this is filled with water. Now tell me, now you you this is, suppose this is glass, this is transparent glass, and what we did, we have taken this and we kept it inside a refrigerator. Okay, we kept it inside of refrigerator. So I am considering this boundary as a refrigerator. Okay, so I am considering this boundary as a refrigerator, and our this we have kept it in this glass, in this. Okay, now tell me, and this is a refrigerator and it is going to cool. This is normal water, this is normal water. Okay, okay, so this is present inside a refrigerator and we are cooling this. Okay, now what you will find here during the cooling, if we focus here, so we will get we will get some kind of nucleation will start before the solidification. Okay, this nucleation will start, and this nucleation will grow slowly. Okay, and we will get ice inside the domain. Okay, so this is the fundamental concept which we have to keep in our mind during the liquid to solid phase transformation. Okay, now now we have seen this transformation is varying with respect to time, right? Now let's try to explore it more. Now if I draw a curve. Okay, now let's take at t equals to 0. At t equals to 0 we have mass of liquid. We are taking it as, let's take this ml. Okay, and mass of solid, it is what, 0. Okay, and let's try to, this is at t equals to 0, and let's define one factor that is called x. This is mass of solid upon mass of solid plus mass of liquid, as we have discussed in dryness fraction. Okay, so can you tell me what will be the value of x at t equals to 0? This will be 0, right? Now at t equals to, okay, and at t equals to t1, here we will get mass of liquid will be 0, and we will get complete mass of solid here. Okay, so let's try to write it here. What will be its value? So this will be what, ms. Now can you tell me what will be the value of x? This will be ms upon 0 plus ms. This will be 1, right? So this, what is t1? This is time required for complete solidification. Okay, and in between I am defining t, I am defining t 0.5. Okay, so t 0.5 is the time when we get x value 0.5. Okay, so we are taking two end points and we are considering one intermediate point where mass of liquid is half of mass of solid. Okay, where we will get 50% we will get liquid and 50% we will get solid. Okay, so this is the variation of this fraction transformation. Okay, this is what x is fraction transformation. X is fraction transformation with respect to time. Okay, now let's try to explore it more. Now just can you write it here? At t equals to 0, what we get? X equals to 0. At t equals to t.5, we get x as 0.5. okay, and at t equals to t1, we will get x as 1. okay, so now let's try to plot this curve. Okay, so this is what this is. This on y-axis we have fraction of transformation. Okay, on t-axis we have time. Now can you tell me what is going to happen? So here initially we will have, at t equals to 0, we will have pure liquid. okay, when we have pure liquid, then we will have time t equals to 0, we will have pure liquid, x value will be 0. okay, now what is going to happen? If the temperature is decreasing, if the temperature is decreasing, then at some interval of time, let's up to here, nucleation will be happening, right? So we call this region nucleation. okay, and after this, we will get the variation of x with respect to time. We will get our curve like this. It will touch here asymptotically. okay, so what we have observed, this is what, let's take it t equals to, this is t0. okay, and this is what at this time we call it t1, or complete solidification time. Here we will get x value as 1. okay, so this is start of solidification t0, and this is end of solidification. We call these extreme point as ts, and this as a tf. okay, and now can you tell me where will be x equals to 0.5? now if I take, this is what 1, this is 0, so this fraction of transformation is varying from 0 to 1. now we will get at x equals to 0.5, at x equals to 0.5, we will get time as t equals to 0.5, and vice versa, at t equals to t 0.5, we will get fraction of transformation as 0.5. okay, now let's try to draw another curve. okay, and one important point, that this curve what we obtain, this line is at a particular temperature. okay, this line is at some particular temperature, right? And from t0, let me write it, at point t0 transformation begins. Okay, and at point t t1 or tf, I am writing this as ts. Transformation begins or transformation starts, and here transformation ends. Okay, so this is what start and final time, right? Now let's try to draw some other curve. Okay, so here on y axis we will take dx by dt. Okay, now you can see this whole transformation curve is at particular temperature, right? This is at temperature T. Now let's try to explore it more. So corresponding to this, we will get this point and extend this line. So what we will get, okay, and here on x-axis we will have temperature, right? So can you tell me what will be the variation of dx by dt? Okay, you can see here slope is increasing. Here from this region to this region slope is increasing. How slope is increasing? If I draw a constant horizontal line, right, just draw a constant horizontal line, you will find that the y value is increasing continuously. Okay, so what does it means? It means that slope is increasing as we are going ahead. Okay, and after reaching this point, here slope will be maximum, and slowly as we proceed further it is going to decrease. Okay, now let's try to draw this curve. So we will get this is nucleation zone, and this is what start of transformation. So we will get this point just before this. Okay, just before this this graph will start, and just after this graph will finish, and in between it will be having some maximum value here. Okay, so let's try to draw this. So we will have maximum value at corresponding to this point. So let's try to draw this. It will be some it will be like normal distribution curve. Okay, so this is variation of uh, of rate of change of transformation dx by dt of this curve, right? So you can see here that as time passes, this transformation is increasing, and at further time it is that slope is decreasing. Okay, but here on x-axis we have kept temperature, right? So this is what for a particular temperature, this temperature is taken as Tm. This is what melting temperature, and before this and in this region temperature will decrease. Okay, so these two graphs are very important. So now let's move ahead. So let's try to explore it more. So first draw the transformation curve. We will get like this. So here this will be what, 0.1. Okay, this is what time t. Okay, and here we will get the S curve. It will start from here and it is going to end, let's suppose, here. We will get this graph like this. So this will be something like S curve. Okay, so it will come here like this and it will increase like this, then it will decrease. Oh, again it is wrong. Okay, so this is some interpolation is happening here, right? So this will be like S curve. Okay, now I think it is better. So this will be like S curve. So this is, just draw one graph here for variation of x, and let's draw another graph here. Okay, so this will be what? So oh, so this will be dx by dt, and here we will plot a graph for normal distribution curve. Okay, so this point will be tm. Okay, this is tm. Okay, and at this temperature, let's take this temperature as T. This is what, Tm, right? Now let's take at some temperature level T, just draw one horizontal line. Okay, we will get like this, and draw for same temperature we have drawn uh, this S curve. Okay, now what is going to happen at this point? Transformation is going to start. Okay, now extrapolate this point and get this point. Okay, and at this point, from this point, transformation is going to end. Okay, so we will get these 2 points. Okay, now let's draw one more graph. So let's draw one more graph here. So on y-axis we will get t, on x-axis we will get ln t. Okay, so what we are going to obtain here, so this line is corresponding to t, and this, let's draw one line corresponding to tm. Tm is the melting point. Okay, below Tm, the solid transformation from liquid to solid, we will get this transformation below Tm. Okay, so we will get this point. Okay, so now if I take another temperature T1 here and draw one horizontal line, okay, now you can see as the temperature is decreasing, the rate of transformation is increasing, right? So this start point we will get some early location from this, and this end point, at this end point we will also get at some early location. Okay, now let's see what is going to happen where dx by dt, where the transformation rate is very high. So I hope you can imagine, if transformation rate is higher, so here it will take very less time to nucleation to start. Okay, and for finishing it will also take very less time. Okay, now what will be happening as we decrease the temperature? You can see the rate of transformation is also decreasing. Okay, So for nucleation we will get a longer time to start, and for ending we will again get a longer time. Okay. Okay, and if at some location we will see, we will get this start point something here, and the end point, it will be asymptotic to Tm, so it will end here. Now let's try to draw these points. Okay, so here it will tends to infinity, and here it will just touch these points. Okay, and here it will be maxima, and again if some point is here in between, then this curve will decrease and it will touch to this, and further it will go like this. Okay, these points are what starting of transformation. Okay, and these red points are finishing of transformation. Okay, so this will be, I have not taken it properly, so it will be like both these curves are called C curve. Okay, because it looks like a C. Okay, and here these lines, it reach asymptotically to melting point. Okay, and this point is called nose of C curve. Now you can see here we are plotting time on x-axis and temperature on y-axis. And what is this? This is transformation, which we are plotting it like this. We are getting in C curve. That's why we call this curve as temperature, then time, and transformation. Right, we call this curve as TTT curve.